Good morning, everyone. Once again, thank you for attending this presentation. My name is Vianney Kambale, as I've indicated before. I am a PhD student at the Klagenfurt University in Austria, and I am supervised by Professor Kyamakya. This is part of the work that I'm researching for my PhD work and together with the rest of the team. The title of this presentation is Ensemble Transfer Learning for Time Series Forecasting, a sensitivity analysis framework for a shallow neural network. So this is the outline of this presentation. I'll provide some background and motivation. I will then speak about what's the problem statement and the research question for this work. Together, we'll go through the state of the art on the work. And next, I will discuss the performance assessment scenario and normalized performance metrics that we are suggesting in this work. And then we will discuss transfer learning performance metrics, and later on also discuss transfer learning efficiency related sensitivity analysis process. And we'll present our experiments and also discuss the result. The research contributions will be elaborated, and then we will end with some concluding remarks. So, time series. We know time series data are ubiquitous, are everywhere, especially with the advent of IoT, with medical data, with electricity data. So time series are almost everywhere. And there is a need for accurate forecasting. There is a need to have accurate predictions of time series on one side. However, on the other side, we also have some of the areas that have insufficient amount of data. Some domains we have enough data, some other domain we don't have enough data. And we know when it comes to applying deep learning, machine learning models, we rely on availability of data. Thankfully, there is a technique called transfer learning that is being researched extensively, and it comes with a promise that is threefold. First of all, it promises to assist in cases where we have insufficient amount of data. And also when we have data drawn from different distribution, it promises to help with some sort of generalization. And also when we use transfer learning, what we can gain also, it's in computational complexity. It reduces computational complexity. And a quick overview of transfer learning. We have on one side what we call the source domain, on the other side what we call the target domain. So the source domain, it's supposed to have enough data. So in that domain, we train the model. Now the idea, a model that has been trained is transferred to another domain that we call the target domain with less amount of data. Now, the transfer learning, obviously, by transferring the model from one domain to another. And what do we transfer really? Actually, we transfer learned weights, from the model from one domain to another. And that's what this work is all about. Now, the reality is transfer learning has been extensively used in other domains like computer vision and natural language processing. In fact, in that area, they've developed even pre-trained models. But when we research literature, we find that theoretical underpinnings of transfer learning in the domain of time series forecasting are still needed. At least that's what survey papers on transfer learning time series forecasting are telling us. And they keep on saying that empirical studies that can determine the advantages of various transfer learning approaches to time series forecasting and to different time series forecasting problems are still needed. That's why in this paper, we want to propose and to investigate the potential of ensemble transfer learning techniques applied to time series forecasting. This is how we define our problem statement. Empirical studies are needed, as I have indicated, to provide insight to which extent different parameters that are used in transfer learning can be effective in the context of time series forecasting. And we set ourselves these 4 research questions. The first question has to do with surveying the state of the art on ensemble transfer learning techniques for time series forecasting. In research question 2, we ask ourselves, can there be some performance metrics and performance scenarios and maybe transfer learning metrics that can be defined, but now in the frame of transfer learning efficiency analysis for time series forecasting? And the third research question that we asked ourselves, how can a comprehensive sensitivity analysis framework for time series for time, framework for transfer learning for time series forecasting performance be framed in the case of a neural network? And the fourth research question that we are posing, to which extent various dimensions and parameters identified in a sensitivity analysis framework can impact the transfer learning process. Okay, so obviously, because transfer learning has been used in many other domains, various work are applying transfer learning to time series forecasting. For example, the work by Chan, Vianney, and Pustia, they proposed a hybridized model that combined deep learning with transfer learning, but using CNN and AI-tuned support vector machine amalgam in addressing short-term load forecasting challenge. And another work that's identified here is 3, proposed a general transfer learning framework. We liked it because it's proposing some sort of sensitivity analysis that is close to the work that we are proposing in this paper. Yeah, and when we survey literature, we find out also that systematically, current works on transfer learning for time series forecasting can be classified as single source domain or multi-source domain. What's the difference? Single source domain, it means we are using only one data set to do the transfer learning. And multi-source domain, we're using various data sets to perform the transfer learning. Now, this is the point. Using single source has got a problem because we can encounter a problem that we refer to as negative transfer. Negative transfer is the phenomenon where when you do transferring, instead of having gain, you get a downgraded result. But that's how multi-source domain approaches came to be interesting. In fact, our work is in that sense because it is ensemble transfer learning method. So despite the many work that have been conducted on transfer learning for time series forecasting, it's evident that there is still a lack of literature on comprehensive study of the impact on the neural network or deep learning design with respect to parameters that can impact the performance of the transfer learning process. So in this work, we want to suggest a few transfer learning metrics, transfer learning matrix. But before we get to that, we started by defining what we refer in our work as normalized error performance metric. You can ask me what it's about. It's simply a combination of RMSE and MAE, but normalized versions that are packed together in a quadratic means format. So the idea is this metric can be robust to the variation when you perform the experiment so many times. So we refer to it as ePerf. And I'm saying ePerf I, you'll understand later when I explain these performance assessment scenarios. So now, obviously, we determine what we call performance assessment scenarios. Where are they? What are they? They will help in our analysis of transfer learning in this work. I indicated before that when we speak transfer learning, we've got the source domain on one side, and we've got the target domain on the other side. And the transfer takes place from the source domain to the target domain. But here we do a couple of combinations. Maybe because of time, I will just explain the table because it explains everything. But let me start with the figure first of all. The model that is used in the source domain here, we are referring to it as model 1. In the target domain, we identify two versions of models. We've got what we call model 2A And this is actually the model that has been pre-trained in the source domain. But we have also another model that we call model 2B. This is a model that did not go through pre-training, okay? So we use this because we want to do a couple of, some experiment. Now, let me explain what we call performance assessment scenarios here. We've got 5 performance assessment scenarios. And the first performance assessment scenario is where we are using, we have model 1, okay? And we are training it with data from the source domain, and we are testing it with data from the source domain. By the way, for simplicity, source domain data we refer to it as with the suffix 1 and target domain with suffix 2. So performance assessment scenario 1, we have a scenario where the model 1 or the target model 1 is trained by the source data, and it is tested by a source data. And when we calculate the performance of that scenario, we call it ePerf1, right? Now, in scenario 2, we are having a model that has been pre-trained, all right? And which means it has been pre-trained first, and then when it gets in the target domain, we continue training with the target data, and we test it using target data. Now we've got a scenario 3 where we have a model that has been trained in the source domain, but now look here, it was trained in the source domain, but we are testing it with the data from the target domain, all right? And scenario 4, we have the model, obviously, that was pre-trained in the source domain. It continued trained in the target domain, but when we do the testing, we test with the data from the source domain, right? And when we calculate the performance, we call it ePerf4. And the the performance assessment scenario 5, it is now that model 2B, all right? A model that did not go through the pre-training, all right? So it's trained by the data that we consider as target data, and it's tested by the data we consider as target data. And we get all these assessment scenario, this performance matrix or ePerf. Remember, that we calculate this way. Now, this lead us to some metrics that we are suggesting to the scientific community that we refer to as transfer learning gain, that we calculate actually by doing the ratio of ePerf5 over ePerf2. Another one, call it transfer learning forgetting ratio. Now, maybe I should explain quickly what is transfer learning forgetting ratio. When we do transfer learning, I initially spoke about the problem that we call negative transfer on one side, but we also have another problem that we call forgetting or catastrophic forgetting. And this has to do with generalization. It means after a model has seen new data, how sometimes if you've seen it, you show it previous data, it completely forgot what it saw previously. It's called catastrophic forgetting. Now, this metric, it will give us a hint on the level of forgettiveness, all right, of the model that has been designed. We also have what we call transfer learning generalization gain. That's when we do the ratio of ePerf3 and ePerf2. And there is another metric that we call reference generalization ratio that we get by doing the ratio of ePerf1 and ePerf3. These metrics that we suggest will make sense if somebody come closer and understand all these assessment scenario properly, right? I will request that you go and read the paper for more details. But actually, this is what we are suggesting. Okay, so this work has been done in the form of a sensitivity analysis process, because remember what we mentioned in our introduction. Survey papers are saying that we still need empirical result, empirical experiments on the effectiveness of transfer learning for time series forecasting. And we thought if we do this in a sensitivity analysis manner, we'll be able to see how the different parameters affect the performance of the transfer learning. Now, because we're in deep learning, so we take, these are the parameters that we think can be studied to see how they affect the performance of the transfer learning. Um, you recognize this a neural network or multi-layer perceptron. So the parameter that can be considered is actually what we call we identify here as the width. Okay, the width actually, if we increase the number of layers, uh, how can that affect the transfer learning? The depth is referred to the number of neurons in a single layer. If we increase or decrease the number of neurons in a single layer, how can that affect the transfer learning result? Okay, here because we are talking time series, the lag. By lag we mean the number of, let's say, number of inputs, the number of values that you give to your network, increasing or decreasing, how can that affect the transfer learning? And also the horizon, alluding to the number of values that you intend to predict. One value, three value, five value, 100 values. And also what we refer to here is the similarity distance or time series characterization, or how similar or dissimilar the data that you consider as source data and the data that you consider as target data, how similar or dissimilar they are. So that can also impact the transfer learning for time series forecasting. But also because our work is on ensemble techniques, there are various ensemble techniques. How can that also impact the transfer learning for time series forecasting? So you understand this is a framework that we are providing, but we cannot go through everything in just a paper. So for this paper, these are the parameters that we have considered. For the ensemble technique, we just using the bagging technique. The number of ensemble instances, the number of learners in an ensemble, we're using for learners. The type of neural network, we start with a simple one, an MLP, right? And we start with a simple one, a shallow MLP. It means we are just considering one hidden layer. And the number, however, when it comes to the number of hidden layer in that, sorry, the number of neuron in the hidden layer, we are varying actually. We consider 1 until 200. These values that you can see on this row. And also we are trying to vary the lag and horizon sizes. You can see the values here. And obviously we are evaluating this our work based on the metrics that we have suggested. I explained them not so long ago. And the similarity measure that we are using is mainly the Pearson distance that we're trying to use to calculate the similarity between the source and the target data set. Okay, quickly, the result, I'll go through the result quickly. Yes, these results are, okay, on the x-axis, we've got the number of layers for different networks. And on the y-axis, we've got the ePerf value, right? So now remember, I explained ePerf 1 to ePerf 5 from the assessment scenarios. So these are the results. But what happens here, it's first of all a trend to show that there is a downward trend, which means as we increase the number of neuron, okay, the model become stronger, all right? The error decreases. And also, now look again, here we remember I spoke about the lag size and horizon size. And then we noticed that actually when the horizon size is smaller, the error is smaller. When the horizon size is bigger, the error actually is quite bigger, but these pictures can say more, just more than that. In the paper, we explain that in most detail. Now, these are some result of the transfer learning matrix that we identify, the TLG, TLFR, TLGG, and RGR. Now, let me just go quickly to the summary. So if I were to highlight a few key points, it is that the transfer learning forgetting ratio for scenarios with Horizon 1 have a lower, with lower lag, are too much prone to forgetting. So Horizon 1 with lower lag are too much prone to forgetting. Whereas when we've got Horizon 1 with bigger lag, they are so prone. I mean they are so robust in terms of forgetting. And we also, let me just, because of time, I can just go quickly to this last discovery. The last discovery, what we identified, we saw that actually the transfer learning gain, okay, are higher for lower number of neurons. So we get a bigger gain, transfer learning gain, when we've got smaller number of neurons. But the problem is the error, or error rather, decrease when you've got bigger number of neurons. Now, there is a need, when you are designing your network, there is a need of trade-off. How much gain do you need to, based on the performance that error performance that you need? And we thought this can be actually one of our further work, try to see how we can design, we can come up with a trade-off with the gain that we need and the performance that we need. All right, so quickly, the contribution of this work are as follows. We have suggested, we've proposed 4 transfer learning metrics that can be used to assess the efficiency of transfer learning process for time series forecasting. And we've given a methodology to perform the sensitivity analysis, okay? Though here we're not able to go through everything, at least there is a framework that can be used, and we provide a use case how to do that. So in conclusion, transfer learning for time series forecasting, it's still too much in its infancy, and we still need more empirical studies to affirm its effectiveness for time series forecasting. And future work, first of all, as I said, trying to see how we can make the trade-off between the gain we want and the performance that we want on one side. But also it will be interesting if we can try complex neural networks models like MLP, but with quite big, with bigger number of hidden layers, but trying also these other networks that you LSTM, CNN, ecosystem network, GANs, and GNN, and with varying all those parameters, it can give us more knowledge when it comes to transferring for time series forecasting. Thank you very much. Uh,